We are right now at the stage where the fluid simulation looks like this. So we can draw solids, and by pressing the space bar we can also draw a bit of the fluids. But of course it's not really sophisticated yet. As you can see, the fluid is not flowing to the side. It is only stacking up, and it's behaving weirdly in places. Yeah, so this so far is just a proof of concept, and I think right now is a good time for, well, if we want to implement an actual fluid simulation, to stick to common knowledge and use this guide right here as a guide. Yeah, we use the guide as a guide. Yeah, and this is a guide about cellular automata and how to implement a 2D liquid simulator. It does not include code, but it does include, well, patterns on how to implement fluids in your project or in cellular automata. And here we have a couple of rules, and if we implement these rules, we should have, as a result, a liquid simulation. So again, we have tried implementing some rules, but they are really complex. Here in simulation step, this bunch of code right here, and all it's really doing is making water fall down, and it's not really something I'm happy about. So this is an odd piece of code, and so let's try to use this as a guideline to actually be able to implement fluid movements. So rule number 1 would be flowing into bottom neighboring cells. So if you have a fluid cell, then it flows down into the bottom cell. Let's have a look at the text. Let me just zoom in a bit for you. First, a cell will check to see if it is capable of flowing downwards into its bottom neighbor. This makes sense, as we want liquid to fall down as if it was affected by gravity. The amount of liquid that is allowed to flow into another cell is calculated based on the amount of liquid already in the source and destination cells. Liquid will only flow if the destination cell has less liquid than the source cell. Liquid will only flow if the destination cell has less liquid than the source cell. Once we have calculated the amount of liquid to flow, we make the adjustment to the liquid value of both cells to reflect the change. The images below from left to right depict how the liquid behaves. Yeah, actually, we have done this already. Or at least we have started to do this in the last episode, where we calculated the amount of liquid flowing into the next cell. But I was wondering about, can we just check the amount of flow of liquid flowing down without considering, for example, the amount of liquid coming in from the sides? So if we look at this cell right here, then liquid is flowing in from the top, but later on we also have liquid flowing in from the sides. Is this something we can ignore right now? I'm not sure. Yeah. But okay, once we have calculated the amount of liquid to flow, we make the adjustment to the liquid value. The liquid falls into the cell below in each iteration until it is unable to fall anymore. Yeah, and let's have a look at rule number 2 already, just in case we have to consider it when implementing. So, flowing into left and right neighboring cells. Once the cell has finished executing the first rule, so first rule has priority apparently. It will then attempt to distribute its remaining liquid toward the left or right neighboring cells. Again, the amount of liquid that is allowed to flow is dependent on the current amount of liquid in each cell. Yeah, and as you can see in the images, the liquid is first flowing downward, then it is checking the left cell. The left cell is a solid block, so nothing can flow there, and then it's checking the right cell, and there's going to be a flow into the right cell. Yeah, and if both neighboring cells are free, then we can let liquid flow into both of the neighboring cells. But as you can see, we can't just forward the entire block of water into the next cell. We have to somehow split it up. So maybe that is going to be a parameter, probably, the viscosity. Yeah, but nevertheless, let's try to take some time and really properly implement rule number 1. Actually, our project already looks as if rule number 1 is implemented here. So liquid is flowing down and stacking up. But when it hits a solid, it's just vanishing. So there's something wrong. And maybe we can redo this simulation step, and if everything is well, then we might be able to get rid of the cell flow, because that is something that complicates things a lot. Do we need a cell flow anywhere? So rule number 3 is describing what happens if the cell is pressurized. That means it has too much liquid in it. Then the liquid will be able to flow up, and that is the only case when liquid ever flows up. But also, apparently, this is executed after rule number 1 and rule number 2. So still no flow needed. And then we determine the flow direction of each cell. Okay, that is not necessary in our case. And then the next thing is just rendering and conclusion. So we actually only have 3 rules. Let's start with number 1. I think we can tear a lot of the code down. Let me just delete whatever I think is not necessary. So I don't think we need any flows. If we need them in a couple of moments, then sorry, we will have to re-implement it, but I don't think, or I think we can do without for now. Maybe the flows would make things more realistic, but I would like to have a fully working fluid simulation before I complicate stuff too much. So simulation step loops over the rows and columns, retrieves the cell, checks whether the cell type is water and whether there's space below. And then let's do a comment here that says rule number 1, water flows down. So if the cell type of the current cell is water and there is space below, let's also check the cell below. So if there is space below, then we will get the next cell below. That is the so-called destination cell. Cell destination cell. And that is the cell in the environment in the environment at coordinate j plus columns multiplied by y. And we increment I by 1 to get the cell below. Okay, so this is the destination cell in this case. Then we check the fill level of the current cell. Let's delete that. And let's answer the question here, how much liquid can flow into the destination cell? And we don't need any flows here. Let me just also delete the other flows. Oh no, let's do that later. So we're in this line of code. And how much liquid can flow down into the destination cell? Ah, that's interesting. First of all, liquid will only flow down. That was part of the rule. Wait, let me reopen it. Liquid will only flow if the destination cell has less liquid than the source cell. Does that make sense? I mean, liquid will always drop down. So if I have a bit of liquid down up here and a lot of liquid in the destination cell, then the bit of liquid will still drop down actually. But okay, let's just implement it and see what happens. Liquid only flows if destination cell has less liquid than the source cell. Let's rename that source cell, the current cell to source cell. So if destination cell dot liquid dot fill state is smaller than the source cell dot fill state, then do something. Now we need to figure out how much free space is there in the destination cell. And we can do this using destination space is equal to destination dot fill state 1 minus destination dot fill state. So that is the destination space as a value between 0 and 1. It's practically a percentage. Then if the destination space is bigger than the source cell dot fill state, then the source cell can completely empty itself into the destination cell. So the source cell dot I think we need to manipulate the source cell directly on the array, otherwise the change won't persist. J plus columns multiplied by I. Then here the fill state is 0. And the destination cell, environment J plus columns multiplied by I plus 1. So the cell below that, fill state increments by the source cell.fill state. Ooh, I'm not sure if I'm manipulating values along the way and thus breaking the code. What is the error here? Is there an error? Let me enable my linter. Oh, there are a lot of errors. Okay, first of all, there's an error here, environment. Then destination cell.fill state does not exist. We have a fill level, however. Fill level. Then destination cell, of course. And then here fill level again, and this is fill level as well, and this as well. And of course, this must be changed to fill level as well. I messed this up everywhere. Okay. Why can't I just increment the fill level of... I'm missing a bracket here. Let's try to compile that. Of course, it doesn't work. Cell above flow. Yeah, now we have to clean up things. So cell above flow. We can pretty much remove all of this code, I would say. And I will keep this nested for loop because we probably have to write all these changes that we're doing. We shouldn't write them into the environment matrix already, because then we would be manipulating the matrix on the go, on the fly, which is not something to do in simulations. You always create one snapshot, calculate the entire next state, and then you copy the next state into the current state. So you act on the entire state instead of on a per cell level. So here we have to do a next environment that will contain the next state. And then we will replace this with next environment next, and this right here as well. So that should be rule number 1. And down here in the for loop, we then copy the changes from the environment next into the environment. And I think this can be a simple array copy by looping over all the indices. So we do environment here, at index is equal to environment next at that same index. So we basically just copy the arrays. There are more efficient ways to do this. So we only copy the array states every second iteration by switching over the arrays with each simulation step, but forget about it. It's not important right now. C is completely fine as it is right now. Okay, and there are some issues. And I don't know where they are coming from. But usually these signs of random points here, they indicate that some array is not completely filled. So here is rule number 1. We get the source cell from the environment, and then we check if the source cell is a water cell. We check that the row counter is not to the last row, and then we retrieve the destination cell. That is fine. Then we check the liquids. That is okay. Destination space is 1 minus that. And then we write the data into the environment. Do we have to maybe initialize the environment using, or the next environment using null? I actually don't think we need to do it, because we should be able to. No, maybe we have to copy first. Yeah, I think we need to copy first. We need to copy the environment into the next environment first, because we are possibly not acting on every cell here yet. So let's just try to do that. Int I is equal 0, I smaller than rows multiplied by columns, I plus plus, and let's copy the environment into environment next, equal to environment. That should work. Okay, yeah, now we don't get these weird issues, and we can still draw things into here. Let's see what happens if we draw a liquid. Okay, we can draw the liquid, but it's not falling down again. That means something is going wrong. So water flows down. Are we actually filling the cell value, or the fill level of the bottom cells? This rule is a bit... No. If the destination cell's fill level is smaller than the source cell fill level, that is fine. Then we check the space in the destination cell. And if the destination space is bigger than... the destination space is 1, probably because the cells below are empty, and the source cell's fill level is 1 as well, so 1 is not bigger than 1. I assume this rule doesn't evaluate. So destination space is bigger or equal. Let's see. Yeah. Oh, and it's even being held by the container, so that's cool. And if we enable the delete button, can we delete these? Right, okay, the water's trickling down. I already like this. Of course, it's not, it's more, so far, it's more like a, well, what is it? The water is behaving like sand, I would say. Not completely, but it's trickling down like that, and then it's stacking up on a small tower. But that should be rule number 1. Water flows down. But I think it's not yet complete, because we only flow down if the destination space is bigger than the source cell's fill level. Can we just flow down in any case? Because if we flow down and the cell below is being overfilled, then we add pressure, and then rule number 3 will resolve this automatically. Let's see what happens if I just remove that if case. Okay, now let's pour some water in here. That's working. I think that's fine. And let's delete some cells here. Yeah, seems to be working. I think we can omit the if case. And that should be rule number 1, water flows down. Okay. Once we have calculated the amount of liquid to flow, we make the adjustment to the liquid value of both cells. Yeah, we haven't really calculated the amount of liquid to flow. We just let everything flow down, regardless of how much there is. Is this a problem? Let's see what happens if we figure out how much liquid can flow. Liquid amount is, well, depends on the source cell fill value. No, actually we know that the source cell fill value is always bigger than the destination cell fill level. That means destination cell fill level. Oh, fill value. Why did I say do fill value there? Fill level. So that's the destination cell fill level. We know this number is bigger than 0 and potentially even bigger than 1, depending on the situation. So we might have to do if liquid amount is bigger than 1, then a bit of liquid has to stay in the source cell. And how much is going to stay in the source cell? Well, we probably just decrement it by 1. And then we know in this case that the next cell's fill level will be 1. So the liquid amount that can flow into the next cell is bigger than 1. Then we decrement it because the next cell is only receiving a liquid amount of 1, and we have to keep the rest. We have to keep the rest in the source cell probably. I'm not sure if it should be that complicated. Probably not. Probably I'm overcomplicating things. Let's see. So here we will set the next cell's fill level to 1. And the current cell's fill level can stay the liquid amount that is left. No, but if this is a very large number, then liquid can only float down. Let's say the number is 50, and it should actually be maximum 1. So the cell is incredibly pressurized. Then through this rule right here, we will only have a single liquid amount flowing down into the bottom cell. Instead of 50, we should let everything flow down actually. No, let's leave it like that. Let's leave it like that. Let's keep it simple. Let's leave it like that. I mean, it worked, or it looked okay in the simulation. So yeah, let's leave it like that. Let's not overcomplicate things. Rule number 2 is flowing into left and right neighboring cells. Flowing into left and right neighboring cells means once the cell has finished executing the first rule, it will then attempt to distribute its remaining liquid toward the left or right neighboring cells. Again, the amount of liquid that is allowed to flow is dependent on the current amount of liquid in each cell. Yeah, so let's just try to implement that. And if we implement that, then it's getting more interesting, because then we will for the first time actually see some water flow. Water flowing left and right. So to do that, we have to check the left and right cells. So the source cell type must of course be water type, and there must be space to the left. Let's just check water flowing to the left right now. So J must be bigger than 0. Then how much liquid can flow to the left? And then we can probably just copy this block of code and paste it here. So we get the destination cell. In this case, it's the one to the left, so J minus 1. And the column is this time... no, the row is the same one, so we keep the I. So that is the destination cell. How much liquid can flow into the destination cell? How much liquid can flow to the left? Destination cell fill level must be smaller than the source cell fill level, which makes sense now. And if that is the case, then let's get the cell to the left, J minus 1, and adapt this to row I. Okay. There's still an error somewhere. What is it? Error expected semicolon in line 112. I recently got a comment. Why are you not using line numbers? Well, because I don't need them. Because, now pay attention, if I press colon, if I press colon and type the line number in Vim, check the bottom left corner, and then hit enter, then it transports me, it beams me into that line number right away, and this is the line. So what's the point of line numbers? I get them in the error message, then I jump to that line number and I don't have to look them up manually. But if I want to look them up, I can also do set number and I will see them, but there's no advantage to seeing the line numbers actually. Yeah. Okay. So let's compile this and check the fluid simulation. Now we should see fluid flowing to the left, although I'm not sure how, if, I think I know what's going to happen. Let's see. Oh my god, no, I didn't know that. What the hell? Yeah, of course. Oh, this is ridiculous. Okay, let's check the logic here. So we completely empty the current cell if there is space on the left, and we completely, and then we fill the column, the cell on the left, which, yeah, that makes no sense. The amount of liquid that is allowed to flow is dependent on the amount of liquid in each cell. So we do, of course, the liquid flows only if the fill level in the destination is smaller than the fill level in the source cell. That is fine. Then maybe it makes sense to introduce a liquid or a fill difference. Let's call it delta fill, and that is equal to the difference between those two variables here, between the different fill levels. And probably it must be source cell fill value first and then destination cell. Destination cell fill level. So that is the difference between both cells' fill value, and how much will flow to the left? Maybe half the difference. So both cells are equalized. So environment next, the current cell's fill level is then decremented by delta fill divided by 2, and the left cell is incremented by delta fill divided by 2. So that should actually equalize the fill levels between both cells. Let's have a look. So here's our solid, and let's draw some fluid. Oh my god. Yeah, I get what's going wrong, but I'm thinking on how to fix it. So yeah, it makes sense that fluid is trying to go to the left, but it should not go to the left mid-air, you know? It should not just... yeah. And it should not multiply on its own. So that makes no sense. So what is going on? Once the cell has finished executing the first rule, it will then attempt to distribute its remaining liquid towards the left or right neighboring cells. The left or right neighboring cells. Again, the amount of liquid that is allowed to flow is dependent on the current amount of liquid in each cell. How do we ensure that the cell is first going down and only then it is flowing to left or right? Do we apply the rules in an if-else statement? So do we apply them only if the cell the first rule has been applied. No, if the first rule is not applicable, try to apply the second rule. Are they exclusive to each other? It's not really straightforward. So we have water flowing left and right. And we are writing these values into the environment, so that is good. I mean, into the environment copy. If we can make this work, the side flowing in this episode, then I'm completely happy. So water flows down. Let's check what happens if we do an else if here. So we're drawing a solid, and now we're drawing water, and it's not flowing to the left. Why? I'm wondering maybe we should introduce a flag that determines whether a rule has applied. For example, let's just do a stupid simple test. I have no idea if this is a good solution. Rule 1 applied is false, and if we apply rule 1, then we set rule 1 applied to 1. This is such a hack. And then we apply rule number 2 only if rule 1 applied, or if it didn't apply. Let's make it if rule number 1 was not applied. Okay, that does not work. And what if rule number 1 was applied? Doesn't work. So I guess this is not a good solution. Why is it not flowing to the left? Rule number 1 is water flows down into the destination cell. Maybe this needs to be done in a completely separate iteration over the entire environment. I'm just looking at this image right here. So the cell flows down. And does this need to be a separate iteration? Or can we do it within the same nested for loop? That is a good question, actually. So we have rule number 2. Probably it needs to be a different loop. Let's just try a different loop. But before we do that, let's just compile and just observe the current behavior again, just to make sure that we know what's currently happening. Okay, it's not flowing left. Then let's create another for loop, another nested for loop. I'm really not sure about this solution, but let's just see. And then we also need to grab the source cell again. Okay, we can paint the solids, and what about... No, this is odd. But somehow I liked it a tiny bit better than the original version, but I don't know why it stacks up. Why does the water stack up so much? Rule number 2, water flowing left or right. How much liquid can flow to the left? So there's a delta fill. That is the difference between the source cell fill level and the destination fill level. Then the environment next will be I'm looking at the environment lines here, and they actually look okay. I mean, the current cell is decremented by half of the fill level, and the next cell is receiving half of the fill level. Something must be very... usually when I have these kinds of issues, it's a very simple solution and I just don't get it. Once the cell has finished executing the first rule, it will then attempt to distribute its remaining liquid towards the left or right neighboring cells. Again, the amount of liquid that is allowed to flow is dependent on the current amount of liquid in each cell. So once the cell has finished executing the first rule, it will then attempt to distribute its remaining liquid towards the left or right neighboring cells. First of all, probably one thing that we can already adopt is that to any cell, left or right, only a third of the liquid flows. Because if we spread the liquid over 3 cells, then it should be thirds in each, not halves. So that is something we can adapt already, even if our code is still faulty. But let me just reappend rule 2 to the original code here. So rule 2. Okay. Then we need to distribute thirds. That is looking interesting. Somehow the cells are really filling upward, which is interesting. What's going on there? Okay, so there's some balancing, which is good. Let's just also implement that rule for the right-hand column. Maybe if we do that, then we gain some additional knowledge on this. And J is smaller than columns. Maybe -1, smaller than columns -1. How much liquid can flow to the right? Then we have the environment value +1 to go to the right. And then there's the destination cell fill level right here. And then there's a delta fill, which is still the same code. And here we have to adapt this to go to the right-hand cell. Let's see how the code looks like now. Ooh. Oh my. That's odd. Of course, the liquid can only flow to the left or right. Let me just comment this, the right hand side handling. Oops. So we're matching the first empty space, the first tab character, and we're replacing it with 2 slashes. Like that. Okay, so we flow to the left, and we can only flow to the left if the destination cell is of type water. Dot type equals water type. Okay, so let's draw this container. Let's put a bit liquid in there. Oh, okay. That looks cool. It's still behaving weirdly, but at least it's respecting the border. Not too bad actually. I don't quite get why the liquid is just floating. Why is it floating down? But this part here is behaving a bit like liquid, just a tiny bit. So what is going wrong? How do we ensure that the water is not floating down to the left or right while it's falling down. Maybe here we have to apply else if. Okay, let's try. No, that still gives us this old result. So this is not else if. So if what? We can only float to the left if the current cell type is water and the left hand, and the cell below us is full. So technically we will have to check if rule 1 applied. Let's see. And rule 1 applied. Maybe like that. It's still floating to the bottom left part. Did I compile? Yes, I did. Check if cell below is either full or solid. Maybe that's something we need to check first. Then, so let's introduce full below full or solid is 0. Oh no, below is full or solid is and we can only do that. It's full or solid, or it's the bottom border. Full or solid or bottom border. So if I is equal to if I plus 1 is equal to rows, or what else? The bottom, no, okay, we're at the bottom row, or the cell below us, the the environment next, 1 second. The environment next cell is full. Or should we check the environment? Maybe we should check the environment. The environment at j plus columns at I multiplied by I plus 1. So the cell below dot fill state is bigger than 1. bigger or equal than 1. Bigger than or equal to, I mean. Or and it's not fill state again, it's fill level. Or the environment at j plus columns multiplied with I plus 1. So again, this is the notation for the cell below. If that cell is of type solid type, only in this case we can actually flow to the sides. So this is a condition for rule 2 to even apply. Maybe we should put rule 2 into that. Ah, so many nested if statements. Yeah, I know. But let's try to get the concept right. Okay, this looks good. Too many if statements. I should nest way more if statements than that if it works. Whatever works. Okay. So here we apply rule 2 for the right hand side. For which side? For the left hand side. And and this is our code for the right hand side. So let's remove the comment here. So we do a string replace. We match the 2 slashes and replace it with a tab. So that gets us the uncommented code. Let's cut that out, paste it. Where do we paste it? We paste it here, and then we indent it, and that should be the right spot. Okay, let's try. Ooh, this looks actually quite good, except I don't like that sometimes the liquid is floating above the rest. But that is the side effect of rule 1, and that is the one that I was trying to fix or that I was considering in the beginning. But as you can see, this behaves like liquid, and it balances out. So this is already quite cool. Let me just make the simulation a bit faster by reducing the frame rate. And let's have a look here. So this is our container. Oops. Come on. Let me just do a new simulation. Okay, are you ready? I am ready. So here's the container. It's not symmetrical. Yeah, everybody's going to be triggered about this. So let's put a bit of water in there. And as you can see, it's not perfect yet, but it's behaving like liquid, at least in some instances. It has a couple of graphic bugs. I don't know where they are coming from. Yeah, let's see what happens if we overflow this container right here. Ooh, that's ugly. Yeah, we definitely need to refine we definitely need to implement also rule number 3, of course, and then we need to refine the rules probably. Let me just make the simulation again a bit slower again, and compile and execute. So here's our container, our cup. Oops. I forgot how to draw after deleting, after the delete mode. Okay. Let me just start from scratch. Oh my god. Maybe I need to add a button to just reset the screen. Okay, so that is the cup. And let's put some water inside. One bug that I can already see is that when the water is falling down, it's already spreading out to the neighbors, which is not correct. But for now, I think this is a good cut-off part where we can say we have an acceptable improvement over the last episode, a very good improvement, because we're actually having a fluid that distributes to the sides. And, well, there's room for improvement, of course. And we're going to implement these improvements in the next episode. So if you're interested, then see you in the next episode. Let me just play around with it one more time. That's the container. Here's the liquid. Yeah, so it's definitely buggy. See you next time in the next episode, where we will make this, or over the next episodes, we will make this a perfect water simulation. You will see. Okay, bye-bye.